Welcome to our webinar on version 5.0 of MIPAR, which we just released a few weeks back. My name is John Sosa, CEO and co-founder here at MIPAR, and I'll be joined by application specialist Dr. Lawrence Small. We look forward to presenting the powerful new deep learning and AI detection features available in our latest release. So first, let's start with a brief introduction to the MIPAR organization. It began as a project at a materials department in a university, was and is continued to be developed by those that use it almost every day. We spun out in 2017 and have spent the last 7 years growing into hundreds of schools and companies worldwide. We're very proud to work with clients both large and small, and we really appreciate those that gave permission to share our partnership today. So today we're going to focus on 3 different areas. First, we'll showcase the new enhancements to our deep learning engine and demonstrate how they can produce higher quality models in less time. We'll then review our latest AI tech, which we call Spotlight, and highlight what its full release brings now that it's out of beta. Finally, we'll cover 2 different workflows where Spotlight and deep learning work together to produce some very powerful yet accessible solutions. Now I'll turn it over to Dr. Lawrence Small to present the new deep learning features. Lawrence?
Thank you, John. I'm very excited to share our new deep learning features with you all. We really have 2 goals. First is to enable our deep learning models to do more, and the second is to produce DL models more quickly. We have 4 different features that I'll go over here today that meet these goals. First is model customization. How can you make the model more powerful for your use case? We have batching and validation. These are training parameters that can make it go faster, that can give you information about how accurate the model is as it's being trained. We have data augmentation, which helps overcome limitations in the amount of training data you might have. And then we have preprocessing recipes to perform transformations on the image that will make subsequent training more effective. So with model customization, the need we're trying to meet is, what if your deep learning model can't recognize the features you need it to, even with lots of training data in time? And the solution can be just to make the model larger. Of course, if your model is larger, it takes more resources to train and apply. You also run the risk of the model simply memorizing the images rather than learning general characteristics of the features you want it to identify. Now, before we get into the actual parameters that MIPAR lets you adjust, let's just do a brief overview of the architecture of a deep learning model, specifically a convolutional neural network. And again, this is just a very high level. I'm leaving out a lot of detail. This is just enough so that you can understand what new parameters MIPAR has exposed. So if you start with an input image here, when a model attempts to classify a particular pixel in the image, it looks at a small window of pixels around that, known as a filter. And it considers this neighborhood when deciding what should this one pixel in the center be classified as. The filter is then scanned across the image to produce an output for each pixel. Now, for technical reasons, these filters actually come in pairs that are applied sequentially. It's known as an encoder-decoder pair. And you can sandwich as many of these pairs of filters together as you'd like. The number of pairs you have is known as the model depth. And these are the new parameters that are available when building a deep learning model in MIPAR. You can adjust the filter size, and you can adjust the depth, the number of filter pairs. So there's a couple of trade-offs when it comes to choosing to increase the filter size or choosing to increase the model depth. If you change the filter size, you change the size of the filter or the size of a texture that your model is really best at identifying. However, if you increase the model depth, you don't so much lose the ability to find small features or find large features, but rather you increase the complexity of features at all length scales. Another consideration is that larger filters give diminishing returns for the amount of compute that you're asking the computer to do. But you don't generally cause training instability if you increase the filter size too much. Whereas very deep models can suffer from the vanishing gradient problem. That's where the training process is trying to reach all the way back through these filters and make decisions about the first couple of layers, and that becomes very difficult. So the model training just becomes ineffective. Of course, I mentioned larger filters can become computationally more expensive as you as you increase the size. Increasing the model depth doesn't so much increase the amount of computations that needs to be done each layer. But the models are less parallelizable because you have to process one layer and then the next, and then the next. And it can take more memory to store all this information. So there aren't any hard and fast rules on which is better for your use case. You might simply have to make some guesses, try different combinations of filter size and model depth until you find a model that really works for your use case. The next need we want to address is, what if your computer resources aren't being utilized efficiently? Right? Say the model and the images simply don't use up all the memory on your GPU, and therefore training takes longer than it otherwise might, or the model simply isn't as powerful as you have the ability to make it. And this can be especially a problem if you're paying for computational resources, or if, for example, you have a very large number of images to train on and you don't want to have to wait until the weekend to do your training. The first solution that we offer is to simply train on multiple images at once. This takes advantage of the highly parallel nature of GPU computation, and it allows you to significantly reduce the number of training iterations you need. But if you allow the model to learn data in larger chunks, there's an increased risk that it can begin to memorize rather than to learn. The second solution that we offer is simply to stop the training early if it's not profitable to keep going. So perhaps you've learned all that you can from the data that you happen to have. So we do this by validating the model outside of the training loop. Just run the model as it currently is on all the training data and give it a score. How well is it doing? And this way you can report how well is the model, how accurate is the model currently. And if it's good enough, you can stop the training. If it's no longer improving, you can stop the training. The trade-off, of course, is that that validation process itself takes time. So you aren't guaranteed to reduce your end-to-end training time, but it is certainly a possibility. Now, the next need we'll address is, what if you only have perhaps a dozen or so images in your training set? This could result in a poor model. It can also result in a highly overfit model, which can process the few images it was trained on, but doesn't know how to handle new images. And a solution is data augmentation. That's where we perform random adjustments to each image to simulate a larger amount of training data. And these random alterations are chosen for each image new every time it's presented to the model. So every epoch, when the training process goes through every image, each image will get a new adjustment made to it. That way you really do amplify significantly the amount of new data that the model is seeing. And it helps the model learn to handle images with a different variation in them. Of course, if you choose a type of augmentation that doesn't occur in your images, you'll be forcing the model to incorporate more flexibility than it really needs to accommodate this. Data augmentation does also take some time to perform. although it's not much relative to the actual training itself. Now let me demo how you would make use of these new features in a deep learning training session. So here we have a data set of leaf epithelium and leaf stomata. So these jigsaw puzzle pieces that you see here are cells from the underside of a leaf. And the leaf has pores in it to allow gas exchange with the environment. We have an example here, one stomata, and another stomata down here in the corner. And we have these pores annotated on 25 different images. Now to see the options, to access the deep learning training options, we have our little wrench icon with a drop down. And these were what were previously available in MIPAR version 4. You can specify the tiling if you want to break the image up into tiles for training. We have a size factor, a number of epochs. If you're not familiar, epochs is the number of times that each image, all the images are presented to the training process. You can also specify the processor that you want training to run on. Our new advanced deep learning training options are available through this advanced training button. And you'll see here in our deep learning options window, 3 tabs across the top. We have model parameters, we have data augmentation, and then training options. So for this particular data set, I've chosen a model depth of 4 and a filter size of 7. For data augmentation, we have some rotation and some shifting that we'll perform. We also allow reflection. And then I'm choosing to add some variation in the grayscale intensity of each image, plus or minus 25 units. So the reason I do this grayscale intensity is because these images have a lot of variation in intensity. So based on the day that the images were taken, how warmed up was the lamp, things like that. So this image is much brighter. This image is bright as well. But these first images are darker. So we add this this grayscale intensity augmentation in order to make the model robust to these intensity changes. And then we have training options here. I'm using a batch size of 1, so only one image, or excuse me, only one tile presented to the training process at a time. Because of the size of the model that I'm using and the particular tiling and size factor, I'm only able to fit the one image at a time on my GPU. So again, size factor and epochs and processor are the same as previously. We also have the option to specify the learning rate. So how fast does the model learn? How large of a jump does the model take each iteration, each time it tries to update itself? So I'm not really talking about this particular feature today, but it is something that's available. And then we have model validation. So every 5 epochs, every 5 times through all the images, the training process will pause, take the model as it currently exists, and then apply to all the images and get a validation accuracy. We also, because you're validating, have the ability to output the best model. So previously at the end of 300 epochs, or if you stopped it early manually, you would just output the model that you had at the end of training. But now, if you can actually validate models throughout training, you can pick the best. That's the one that you receive at the end. We also have an early stop patience. So if you've gone through 10 validation rounds and you have not seen any improvement in the model, then you can go ahead and stop the training early, automatically. and then we'll discuss pre-processing recipes here in a second. So perform this training, I hit train new, and then it took about 6 hours for the training to complete. On my particular system, I have a 1080 Ti. It's not top of the line or anything, but it was able to train in that amount of time. And then if we apply the model, and we'll open it up in the image processor and open up an apply model step to start the recipe building, and you'll see that it didn't do very well. After a bit of investigation, it turns out the reason the model isn't doing very well is because there was too much grayscale variation, just making things more difficult. So we'll return now to the slideshow and demonstrate how I use pre-processing recipes in order to fix this. Now the last feature that I'll highlight today is pre-processing recipes. And in some ways this is the opposite of data augmentation. Perhaps in your images there's a difference in illumination, or there's shading variation across the image, and you can remove this variation with pre-processing. With our new pre-processing feature, you can package some grayscale processing into a recipe, and then set that recipe as an option in the training. This recipe is then automatically run on each image before the training begins, and MIPAR will also store this recipe along with the resulting model, so the pre-processing is applied automatically when you use the model in a recipe later. Of course, that pre-processing needs to be well designed. For example, if you have an auto contrast step but then feed it in an image with no features, the auto contrast will blow any noise in your image to cover the whole grayscale brightness range. So you do need to be intelligent about how you design your pre-processing. Now let's return to our leaf stomata dataset. I can demonstrate the power of pre-processing your images. So if we open up one of our images here in the image processor, where it's where you build recipes and such, I built this pre-processing recipe. And it's very simple. All it does is do an auto contrast adjustment here, and then a non-local means, which is a noise reduction. And that's it. You save this recipe. And if we return to our session processor, in our advanced options, we can load the pre-processing recipe here, just like so. I also, for this particular training run, turned off the grayscale data augmentation, because that's no longer appropriate when we're pre-processing the recipe. And now, when you train the model, it will first pre-process all your images with this recipe, and then begin the training. We load in the model that results. And actually, the previous training that you saw ran for 6 hours. This training I stopped after just 1 hour. And if we apply the model here, we will see you get much better results. Give it a second. And wow, we have that stomata actually highlighted very clearly here. So this is our apply model user interface, and the pre-processing recipe is shown here. This is the one used for training. If something happens, if you have a new batch of images that are imaged in a new way, and you wish to perform a different kind of pre-processing, perhaps you want to bring your new images and make them look like your old images, you can choose a different recipe here when you're applying the model, and this new pre-processing will be saved in the recipe as what you're actually choosing. That way, if something changes, you can use this pre-processing to keep your old model relevant. And it's applied automatically every time you run this apply model step. Now, the last thing I'd like to cover today is some new features that we have in the pipeline. The first is the ability to select which model architecture you want to use. Currently, we offer SegNet models, but UNet and perhaps others will be available soon. We also plan to allow the import of outside models, for example, Onyx or PyTorch. And an upcoming extension of our new validation feature is to select some training images just for validation, so they aren't used for training itself. When combined with the setting to output the best validating model, this will go a long way to reducing the risk of overfitting if you're actually outputting the model that does best on new images that it hasn't been trained on. We also plan to let the training stop automatically when a target accuracy is reached. This, of course, will save training time. And again, it will reduce overfitting by not giving the model time to memorize training data. As soon as it gets good enough and it's really learned the easy features to learn, stop the training. And a final feature I'll highlight is the ability to train on images with more than 3 color channels. Currently, those images have to be converted to grayscale before training, but we'll be removing that restriction soon. And John, I'll turn it back over to you.
Thanks, Lawrence. So first I want to start with a quick overview of Spotlight for those unfamiliar. As I hope you'll see, it is a groundbreaking generalized artificial intelligence software that enables systems to see objects of all kinds, much like humans do, even and especially if it's never been specifically trained on what you're showing it. Now, the most important part is how we've integrated it with the rest of the platform. It's been integrated in 2 ways. The first is the automated recipe step available in the image processor, named Spotlight itself. As an example, here is a grain structure we'd like to segment. We can simply open Spotlight from the image processor and use its default grid mode, where each green dot will prompt Spotlight to look for a feature beneath it. With default settings, the image will be analyzed in this example, and the feature segmented. And we've seen this work remarkably well on all kinds of applications. The second is an intelligent drawing tool named Snap. It's available anywhere there are drawing tools, including in the manual edit tool in the image processor, and the session processor for mass editing and deep learning training. Here we see it working. In point mode, hover objects and it sees them, click to select. In box mode, click and drag around your feature of interest, release to select. This tool can be incredibly useful for manual intervention in recipes, post-recipe cleanup in the session processor, and accelerated yet precise tracing for deep learning training. So with Spotlight now out of beta in version 5, there are a few notable enhancements. First, performance has seen an overall improvement from the 4.5 beta release, and it's now fully supported on Windows 10, 11, and Server 22, as well as on all Apple Silicon Macs running Mac OS 12.6 or higher. It still remains most performant on Windows systems, and for those we strongly recommend an NVIDIA GPU with at least 6 gigs, but preferably 12 to 16 gigs of RAM. In our user manual, which you can reach from the user resources menu on our website, MIPAR.us, you'll find a table of GPU options sorted by performance class. Once you're at the user manual, just search AI training requirements and it's the first hit, or you can also scroll down to the session processor section and click the AI training system requirements page. So now I'd like to demonstrate 2 powerful workflows which combine deep learning and Spotlight. The first is using Spotlight to refine a deep learning selection. In this example, we're going to look at the segmentation of a weld bead. You'll see how we can use Snap, first of all, to make the annotations of the different features in order to train the deep learning model. I'll show in this example some adjustment of deep learning settings which are now possible in order to train the best possible model. And then you'll see how Spotlight can take the probability map suggestions in the middle here produced by the deep learning model and clean up the results for optimum accuracy and consistency. So let's get into the demo. So let's say you're working on an application where you need to automatically detect the cross-section of a weld bead, or any feature for that matter, and perform some dimensional analysis on it, such as looking at a depth profile or a maximum height or maximum width. Today we're going to get into the segmentation aspect, the detection aspect of that solution. The most straightforward way that we recommend users tackle this problem today is with a combination of deep learning and Spotlight. Using our session processor to train a deep learning model to roughly select the feature of interest, and then use Spotlight to refine the selection, improve consistency and robustness. So let's take a look at the full workflow here. In MIPAR, we're going to start in the AI session processor, which you have available if you have the deep learning extension. And what we'll do first is just add the images to train the model on. Now we're going to go ahead and add 3 layers here to then use Snap for annotation. So with the layers selected or generated, we can then start making our tracings. We'll start in the weld layer. We'll go up here and activate the Snap tool. And the default settings that I have here are fine. You can switch between our fast and our accurate model, point or box mode, as you saw earlier in the presentation. The feature scale controls the size scale of what it's going to target. 1 is generally a good option. Auto can also work for you. Adjust as needed based on your features of interest. So now here, as I just hover my mouse, it's going to be looking for features to select. I'm just going to click here to select my weld. I'm going to turn on autosave. Now I'm just going to click through the images and do the same thing. Now I can switch over to the background. I don't need to grab all of it, just the majority is fine. And then I can go for the substrate. So in less than a minute, I have selected my features for deep learning training. Now, what I can do is go ahead and set up some training parameters. And here we can explore some of the flexibility that our new settings give us. To start, well, let me first save the session here. So I'll say save session. And now I can expand my settings. So for this application, I really need to consider the entire spatial contents of the image, and thus I do not want to split it into subtiles. So we'll use 1 by 1 for the tiling. I'll go with the 0.5 size factor, which will just reduce the model size or the image size used for training by a factor of 1/2. It does not disrupt the model's ability to work on the full resolution images. All of the resizing that needs to happen during training and then during execution happens for you automatically in the background. So I'm going to use the 0.5 factor. This will let me speed up training a bit, reduce memory demand, and since I'm going to be using Spotlight to refine the selection, I'm ultimately not concerned with very precise resolution of the model. Epochs, I like to use 150 these days as a starting point, and as you'll see with the, or as you saw, rather, with the early stop availability when validation is turned on, you can be much less concerned about wasting time and resources by having your epochs too high. So generally, set it to a good high number, and when you turn on validation, if it's reached maximum accuracy, before then, it'll stop itself. So now I'm going to go into the advanced settings. Now here, for this type of application, what I've learned is that both an adjustment to filter size and model depth can make a strong impact here. So I like to keep the filter size at odd numbers. I used 7 for this example. I just needed a bit more context awareness for the model to understand when it's in the center of the weld bead that is still part of the weld bead, even though it can't necessarily see the edges. And then for model depth, I needed to go up to 6 and just raise the size, raise the complexity of the model to have it learn what it needs to learn about what distinguishes these different areas from one another. I used default data augmentation parameters, and for training options, I left everything as default with validation turned on, and then I said early stop after 2 validations execute without change. So I can accept that, resave my session, so all of my adjusted deep learning settings are now part of the session, and go ahead and train the model. So this will now begin the training. You'll see the training spin up, and you'll get an estimated time here. And you'll see now the accuracy also change with validation on as it proceeds. So in roughly 4 to 5 minutes, this model will be trained, and then we can take a look at applying it and cleaning up the results with Spotlight. So here the early stop was triggered. In fact, it only ran for 2 minutes of training time, just over 2 minutes, and we see the final accuracy reported here. Now, to go ahead and run this model and turn it into a full recipe with the aid of Spotlight, we'll just go ahead and first save the model. I like to put it inside the session folder. Model is a default name. You're advised to name it with perhaps some of the settings that were used. If you want to try different iterations, name the model with those settings so you can easily tell them apart. For now, I'll just accept the default name. Then we can just push apply model, which will open the image processor, load this image, and run the model. So there we see a high quality model for the purpose that we're designing it for. It's a rough selection where you get different probability maps now for your different layers that you've trained. Wherever it is brightest in each probability map is where it thinks pixels of that feature are most likely to be. So in our weld map, we see a nice collection of bright pixels around the weld. Now, we certainly don't have the type of edge precision we need to get accurate shape and size measurements of a feature like this, but we are only using this deep learning model to roughly target where the feature is, and then we'll use Spotlight to get an accurate selection. So I will accept this model, and then I will go and select from the probability map the portion that I'd like to use. For that, I'll use a basic threshold and slide this up here to something like that. Now I can only keep the largest feature in the image with a relative size filter. that will discard everything else but this large feature of interest. Then I'm going to put this into any memory slot. Could be the companion, could be any of these other memory slots. This will let me use the custom prompting mode in Spotlight, where I draw from the contents of memory images to provide my prompts. Once this is set up now, I can just go right into Spotlight, and this will by default work on the original image, so I can call it right after setting the companion. Since the companion is the only memory image, it will default to that memory image for selection, and it will also automatically switch you from grid mode into custom. The only thing I'm going to change is to use boxes instead of centers. So this will use a bounding box of each of my features in my memory image as prompts. And for this, I also decided to use the auto feature scale setting. If I hit perform, it's now going to reload the Spotlight model into memory since it was removed for deep learning purposes, and then apply it. That loading process will be skipped now every time you use Spotlight going forward. If I open this back up, you'll see you won't need to load that model to memory again. It will simply run Spotlight using that bounding box and refine your selection. So we can save this recipe now. And then we can try it out on each of the other images. So we can choose Open Image and Reload Recipe, and choose one of the other images. We see a quality result. If we check in on the performance of the deep learning model on this feature, again, we have a nice, bright, but rough selection that Spotlight cleans up. Let's try it on the third image. Again here, not a selection that you'd want to use for segmentation on its own, but perfect for use with a Spotlight cleanup. So of course you'd want to ultimately run this on images outside of the training set. We've seen high success rates with this type of workflow for many different applications. And now we'll head back to the slides and get into the other workflow which combines deep learning and Spotlight. So that was a workflow where Spotlight was used following the execution of a deep learning model to clean it up. Now I'd like to present one where Spotlight can be used before the deep learning model to automate and dramatically accelerate the labeling of features across thousands of images necessary for deep learning training, and thus lead to highly robust models which are traced and trained while you sleep. Here I'm going to leverage a new tool that we're going to be releasing in version 5.01 this Friday, which lets you split images into separate tiles. It turns out that Spotlight's resolution vastly improves as you crop in on features, and the tiling component of this workflow is going to take advantage of that. So let's get into the demo. So let's say we have a collection of grain images here, which represent different samples, different appearances, different microscopes, different sample prep conditions, different imaging conditions. Here I'm just using 4 as an example of this workflow. We've actually used this workflow to train a model on many more, which I will show the execution of after demonstrating the workflow for training. So, yes, we have shown that Spotlight could be used on its own to develop a robust universal grain segmentation solution, which could be set up to work quite well across cases like these. But an alternative is to use Spotlight to, as I mentioned, automate the tracing or automate the labeling of these features to train a deep learning model, which at times can be even more robust and more performant than a pure Spotlight solution, especially in finer grained cases or where you have a mixture of coarse and fine grains across the sample. Because deep learning is not prompt-based, it can be much more effective at quickly identifying features of interest. And the use of Spotlight, as you'll see, can be instrumental in automating the most laborious portion of any deep learning model training, which is the annotation. So let's take a look at the workflow from start to finish, and then we'll look at the results. What I'm going to do first is, from any app, launch the new tiling tool, which, as I mentioned, will be released in version 5.01, out in just a few days. From any application, under the Tools menu, we can go into the Image Tile Extractor. Here we just get a small utility, which lets us add any number of images or folders containing images, decide where the tiles should be output, and how many tiles we want to create. As I mentioned before, Spotlight's resolution improves dramatically as you crop in on an image. So take the same pixel content, same image content, but make it occupy a smaller fraction of the overall field of view, and Spotlight then interprets the image a bit differently and can more effectively select the finer features in the image. So to take advantage of that, we are going to pre-tile all of our images for training using this tool. So I'm going to drag and drop those 4 images that you saw just a moment ago. We will then have their output directory be by default where the images came from, which is fine. You can of course change this either by clicking browse or typing in a different path. And in this location there'll be a folder created called image tiles. And in this example I'm just going to use 2x2 tiling, so each of these 4 images will be split up into 4 images themselves, giving us a total of 16. It confirms the number that were extracted. And then inside of the tile folder, we will see the following. So here we see each image split up into its 4 small sections. Now we are going to use these tiles and Spotlight to develop an automated tracing recipe. We'll come back to the session processor to train the model. So here in the image processor, let's begin by developing our tracing recipe. I'll start with this one here. Now, in some cases, I've had good success in taking one of the smaller pixel size tiles and putting a resize step at the top of the recipe to force all tiles, regardless of what image they came from, to be the same, at least X number of pixels across. This has allowed certain parameters in the automated tracing recipe, like erosions and dilations, to have consistent results, and has helped accommodate, or has helped allow the model to accommodate, different magnifications and resolutions. So that's what I'm going to start with here. Under resize image, I'm going to put in 300 and empty out the Y, and the Y will automatically be set to whatever keeps the aspect ratio consistent. Now here I'm going to fire up Spotlight, and I'll choose a grid density which I know will work just fine for almost any case I throw at it here. So this will select our grains, or most of the grains, very nicely for us, especially once we've tiled it like we have. Now I want to select the boundaries as another class. Now I can't just invert because there could be missing grains, and I don't want to call all of that missing grain the boundary class. It's not significant if there are missing grains, as long as we accommodate them when we're identifying the boundary class. So to do that, I'm going to first invert my result. In fact, let me take a different approach. What I'm going to do is dilate my result by 3 pixels and then shrink it back down. That will close off all of my boundaries, but leave these missing grain gaps intact. Now I want to select only the boundary class after I have set up this closed condition. So I need to go back to how the image looked in this step. That's what memory images are for. So I'm going to set step 2 as a memory image so that I can recall it. Now I'm going to actually take this state and set it as my companion, because I'm going to intersect this closed off state with the inverse of this image. This will capture my boundaries for me. So if I set this as my companion, then I can call my first memory image, invert it, and do an intersection. An intersection now will operate between the current image and the most recently set companion image, which is this. That now gives me my boundary class. So now I can set my layers here on the Spotlight step, or where I have my grains. And here in my intersection step, I have my boundaries. And now I've set up a recipe which will trace my features for me. I'll go ahead and save this. I'm going to call it Auto Trace. Let me now try this out on a few tiles from the other examples to make sure it does a nice job tracing. We'll try one from this example. This one here. And this one here. So we can now hand the deep learning engine 10, 100, 1,000, 10,000 tiles and have it automate the annotation of the grains for us quite nicely, where really only the confident grains are going to be selected by Spotlight, which is just fine given the massive data we're going to be handing it. And then we'll take the resulting model and we'll apply it to the full-size, uncropped images. So let's get into that. In the AI session processor, or excuse me, let's start in the batch processor. Here we're going to load our auto trace recipe. And we're then going to give it all of the tiles that we have extracted. Now it's going to output a session for us. We can leave the default name, or we can give it something else. And we'll click process. So for these 16 images to automate their tracing, it's taking just about 30 seconds. That, of course, is substantially quicker than one could trace these by hand. Once finished, we can click View Results, which will open the session in the session processor. And we see high quality annotations across all of our tiles and all of our images. So now, again, I could set up my training. Since I've already tiled my original images into these tiles, there's no need to tile further, so I'm going to go one by one. I care a bit more about resolution in this case, so I'm going to use a size factor of 1, my epochs of 150, and as before, I stay with the default model depth and filter size, and I used 2 for the early stop patients. Now we actually trained a model just like this on over 2,000 tiles across many different grain images and are working towards an effective master grain model. So what I'd like to do now is show you the performance of that model and how it gets quickly developed into a very effective recipe. And then we'll try that out on some images that are entirely outside of the training data set. So we'll go back into the image processor now. And I'm going to open one of the full-sized images. So first I'm going to run the full model that's been trained on over 2,000 tiles. To do that quickly, you can simply take the model file from your file explorer and drag and drop it into the image processor. So this opens and runs the model. Now, the only parameter that sometimes we've needed to change has been the size factor. If we adjust this down, we likely will get a better probability map. And in fact, a size factor of 0.5 has made this model work optimally for most grain cases. But this is how you could tune the model to work better on your given resolution or magnification if it doesn't work optimally out of the box, just adjusting this simple factor. So we see what is representative of a very high quality model near black and white in the probability map, where it's very clear what it thinks are grain interiors and grain boundaries. All of these light gray streaks are in fact part of the grain, so we can easily set our probability threshold to not include those as separations. So again, back to thresholding on the deep learning result. Something like this, which now will give a very good selection. You'll see how all of this will be cleaned up in a moment. One thing that I like to add to a selection like this prior to cleaning it up is a very small separate features in case you have 1, 2, or 3 pixel connections between selected areas. Separate features with the right settings can break those up without over separating along pieces like this. So under morphology, we can just set this to 5. So this will only allow separations to be drawn if they are 5 pixels or less. I like to use 1 as a standard separation, and that's just sort of a safety net to make sure that, again, very minor pixel connections between features are broken. Next, I'm just going to eliminate any noise features. Anything under 20 pixels tends to be a good rule of thumb. So under reject features, just use the default setup, perform, that eliminates any features that are 20 pixels or less. And lastly, I'm going to add a clean boundaries, which will take this selection and expand them out until they touch. Switch over to labels view for the best visualization of grain separation, in my opinion. I like the color cube map. And now we have a cleaned up grain segmentation based almost entirely on this robust deep learning model, which has been trained with automated spotlight tracings. So let's save this recipe and try it out on several other cases. Well, it's not always the case that images within the training set perform well with the model, but perhaps unsurprisingly in this case, all of the images that we have tried were part of the training data and have performed very well. So let's go find an image that was entirely outside of the training set. I went out and found a new grain image, and we can load it here. And we see a very nice result. Again, this image was entirely outside of the training set. And if we take a look at how the deep learning model has interpreted things, it's giving us the kind of performance we're looking for. Perhaps if you're fine-tuning this for your image, you set a slightly different probability threshold, or again, play with the size factor, but very minimal modifications, if any, can now lead to very accurate and very accessible automated solutions. So we're very excited about this workflow. Not only are the tracings high precision through the use of Spotlight, but they're of course fully automated. This really allows large training sets to be used without tedious manual annotation, and has produced some extremely high quality and robust models. So there you saw two powerful ways that deep learning and Spotlight can work together. One where Spotlight cleaned up what deep learning found, the other where it was used to help train the model itself. And yes, you could use both at the same time. Spotlight to help train a deep learning model, and then again to clean up what it finds. Now, depending on what version you're coming from, there may be several other features new to you in version 5 that we didn't get a chance to cover today. For one, batch processing can now be paused and resumed on demand. Even if you pull the plug on your workstation mid-batch, after booting back up, you can pick up right where you left off without losing any work. PDF and Word reports for those with the report extension can now be automatically generated upon batch completion, and you can configure the settings of the report in a report settings panel prior to running the batch. And now MIPAR, including everything you've seen today, is now natively supported on Apple Silicon Macs, which now enjoy a significant boost in performance. So how can you start using these features? Well, for those under active maintenance, regardless of what version you're on today, You can upgrade to version 5 by visiting MIPAR.us/download. There, after choosing your operating system, you can download a full installer of version 5. If you have Spotlight on your license, the Spotlight extension, you'll also need to run the new Spotlight installer after running the version 5 installer. You can download this Spotlight installer from the same place. Just select the Spotlight tab on the download page after choosing your operating system. Once you run the installers, you're all set. There's no need to uninstall the previous version. If you're out of maintenance, contact our support team at support@mipar.us to learn your renewal options. Ordinarily, it's a higher rate to renew expired maintenance, but through the end of the year, we're going to be running a promotion where expired renewals will receive the reduced rate. And if you don't have either the deep learning or Spotlight extensions on your license, but you're interested, also please send an email to our support team at support@mipar.us, and we'll be more than happy to get you set up with an evaluation and pricing options. Now we'll get into the Q&A. Please give us just a moment to review the questions that came in, and feel free to ask any in the chat right now.
I see a question from Jose. How did I determine that the grayscale intensity was the issue in the first model? Really, it was just a matter of trial and error. That was the thing that I tried fixing was perhaps the model's having to do too much. Well, when the model isn't very good at identification, you try to, the goal or the strategy you have often is to try to make it do less. And so that was the thing that I tried that really worked. There's not really much more to it other than trial and error. We have a question from Frederick. Will we send a link to the webinar? The answer is yes. Everyone will get a replay webinar link here in a little bit. It'll come through in an email to you. And a question from Marcel. When you add a pre-processing recipe before training, do you need to train a new model from scratch, or can you update a previous one? You can update a previous one. It's not necessary to train a new model. So when you look at all the advanced settings, really it's the model parameters, the filter size, and the model depth that cannot be changed when you're updating a recipe. The other ones, whether it's pre-processing or batch size or validation or data augmentation, those can all be changed freely between building your model and updating or initially training your model and updating it. So yes, you can add a pre-processing recipe and update the model.
And as Lawrence showed, if you are not looking to necessarily update the model training with pre-processed data, you simply want to stick a pre-processing recipe before the model and have both the pre-processing and model run in a single apply deep learning step, then as he showed, you can open apply model in the image processor, load the model that you have, add a pre-processing recipe to that step, and then add that step to the recipe.
Right, if you're not interested in actually updating the model itself.
Correct.
Thanks for that, John. We really do put a lot of effort into making sure the MIPAR is state of the art and also very easy to use. So I'm glad you like it.
Okay, well, if there are no more questions, then we're going to close up. If any come to mind, feel free always to shoot our support team an email at support@mipar.us. You can also reach us by phone or chat by visiting our website. Go to the contact section. And thank you all very much for your attention and for being MIPAR users. We look forward to continue seeing what you can do with the software. Have a great day, everyone.